for the invitation. So I'm not entirely sure what's the background of this audience. So I'll try to be telegraphic at times and try to focus on things that maybe more of you can understand, but please interrupt me if I say things that are way above your head, and I'll try to fill in the necessary details. On the other hand, I can't give a full introduction to string theory because otherwise we'll never get to AdS. Okay, so what is this about? So this is something that has played an important role in string theory in the last 20, 25, 30 years. And what's the basic idea? So the paradigm example is that you look at string theory, whatever that is, and I'm not going to explain it in enormous detail, on say AdS 5 cross S5. And the claim is that string theory on AdS 5 cross S5 is somehow the same as n equals to 4 2-pi Mills, which is a quantum field theory in 4 dimensions. And so in order to say what you mean by this duality, you have to explain a little bit how the two sides are related to one another. So on the gauge theory side, what we have in mind is we are taking an SUN gauge group. So I mean, I'm not going to explain to you in detail what 2-pi Mills theory is, but it's basically a gauge theory with some non-abelian Lie algebra symmetry, and the Lie algebra symmetry in question is SUN. So this side is characterized by two parameters, namely the coupling constants of Young-Mills and the rank of the gauge group. So these are the parameters that appear on the quantum field theory side. And on the string theory side, well, AdS 5 is the space that's characterized by x1 squared plus x4 squared minus x0 squared minus x minus 1 squared is equal to minus r squared. It's a hyperboloid embedded in one dimension higher. So it's characterized by a length scale, by a radius, or the inverse of the curvature. So the parameters on this side is the string coupling constant. The string coupling constant is the measure for the strength at which a string can split into two and join again. So it's like the coupling constant of the gauge theory. So that's one parameter of the string theory. And the other parameter of the string theory is this radius. This radius describing you the size of the AdS space. And in fact, it has to be also the size of the 5 sphere. The 5 sphere is just the space x1 squared up to x6 squared is equal to r squared, with r the same parameter. So when you say that these two things are the same, you have to explain how these parameters are related to these parameters. Because, I mean, you have two types of different descriptions, and in order that they are the same, you have to say how they're related to one another. Now, this duality is an interesting duality in that the relation between these parameters is not a totally obvious one. So the correspondence says that the string coupling constant is related to 1 over n to the inverse of the rank of the gauge group. And then the other characterization, so what this tells you is that we want to be at large n, and as you may know, SUN gauge theory at large n simplifies, because in this double line notation of 't Hooft, then at large n, the only Feynman diagrams that dominate are those that you can draw on a plane. So this is the so-called planar limit, and you may have heard that this theory becomes integrable in the planar limit, so good things happen to you in the large n limit. So we're going to look at the large n limit, which means perturbative string theory, which means the coupling constant of string theory is small. So the probability of the string splitting into two is relatively small. Now, if you know a little bit about large n gauge theories, then you know that at large n there is an effective coupling constant that characterizes the gauge theory in this large n limit, and that's the so-called 't Hooft parameter, which is g squared Young-Mills times n. This is the so-called 't Hooft parameter, which is the effective coupling constant in the large n limit of this gauge theory. And this, under this correspondence, is to be identified with the radius of the AdS space in terms of the string length. The string length is the natural length, the natural size of the string. So these are the way in which this correspondence works. The two parameters on this side and the two parameters on this side are related to one another in this fashion. Yes.
Sorry, but the LS is the third parameter, or is it for what they...
Well, LS is sort of an intrinsic parameter of the string theory. It's the string tension. It's the...
So there is one more parameter on the string side.
Well, yeah, I guess if you wish that, but it's only this ratio that matters on the string side.
So a priori on the string side, there's 3 parameters, and on the gauge side 2.
Like on the string side, we have 2 parameters where one is GS and the other is effectively R over LS.
R over, yes.
Okay. Yeah.
I think so it's the rate, I mean, there is no overall scale of the string size. The only thing that matters is the size of the space in terms of the string size. So that's the correspondence between the parameters on the two sides. And what this tells you is that, so people often say the AdS CFT duality is a strong weak duality. So what do they mean by that? So if you take n to infinity, which is what I said is the natural thing to do in order for this to be the 't Hooft coupling constant, then if lambda is small, which is what perturbative gauge theory is like, what this corresponds to is that the radius is of the same order as the string length. I mean, so obviously these relations you shouldn't take literally. These are relations that are true in the supergravity limit. They are true if this parameter is large, and so this relation is not to be taken literally, but what it means is if this is small, then this has to be small, which means the radius of the space has to be of the same size as the size of the string. I mean, the string can't really be bigger than the space in which it propagates. So what it really means is that the string, the typical size of the string is the same size as the space in which it propagates, and that is the opposite to the supergravity limit. So that's the limit, that's the regime where the string is very, very large, whereas the supergravity limit is the limit in which the string is basically a point-like particle, and you can describe string theory in terms of effective field theory, namely supergravity. So this is the limit that's the opposite of supergravity. So the supergravity limit of string theory is the limit in which the string is tiny, and then it's basically a point particle, and you can pretend that it wasn't a string. But the regime where super Mills is perturbative is exactly the opposite to it. And since string theorists, by and large, only know how to do supergravity, this means it's a strong weak duality, which is a euphemism for saying I can calculate this side, but I have no clue about this side. This is basically what strong weak duality means. Or conversely, if you look at a regime where the radius is much bigger than the string length, then you can use supergravity to calculate the string side, but then you have no clue how to calculate the Young-Mills side because it's strongly coupled. And strongly coupled gauge theory you don't know how to solve. So that's why people normally say it's a strong weak duality. And that's the reason why it's so hard to prove the AdS CFT duality, because in the typical regime you either have this side under control or you have this side under control, but you don't have both sides at the same time under control, which would allow you to prove it. Now, our strategy of trying to prove it is, there's not really much choice. I mean, if you want to prove it, you have to stay within this regime because you don't know how to do strongly coupled gauge theory, full stop. So here you would say it's the opposite to the supergravity regime, so obviously supergravity will not be good, but you could ask, maybe there's some redeeming feature that will turn the string theory side solvable in the regime where the radius is of the same length as the string scale. So maybe something else could happen. Something special must happen because it corresponds to basically weakly coupled or essentially free super-Mills theory. Now the idea, and I should have probably started out by saying that what I'm describing is work that I've done together with Rajesh Gopakuma. And this goes back already a number of years, and then more recently, it's also involved my student Lawrence Eberhardt, or my former student. Our idea is that the perturbative regime there should be something special happening here, and what should be special is that you don't have a supergravity description, but maybe the worldsheet description of string theory becomes solvable. So the idea is that it has a solvable worldsheet description.
supergravity regime is also n equal to infinity.
Well, yeah, I mean the supergravity regime, yes, in some sense, n equals to infinity only determines whether the string coupling constant is strong or weak. So if you want to be in a regime where your perturbative string theory, you want to be in the supergravity regime, you also have to take n to infinity. But then the supergravity regime is that this is large, and the gauge theory regime is that this is small. So if you want to be in the regime of perturbative gauge theory, you have to take this being small. So you know supergravity is out of the window, but we can ask, is there something else that allows you to solve string theory in that regime? And then somehow there must be. You see, this theory is very, very simple. I mean, certainly when you take lambda equal to 0, this theory becomes very simple. It's a free field theory, a free quantum field theory. So you can solve it. I mean, you can, this is in some sense a trivial quantum field theory. It has enormous symmetries. So there must be something special happening on this side. Now, you won't see the special thing happening in the supergravity description, but the honest description of string theory is in terms of a worldsheet theory. It's in terms of maps from the worldsheet into the target space. But you have to look at the honest worldsheet description, and what you expect is that that regime should correspond to a very special worldsheet description which reflects the enormous symmetry that this theory has. That's sort of the ideology. Now, obviously, ideology is ideology, so I can tell you whatever I want, and I mean, maybe that's a convincing argument, but if I can't deliver, then it's not going to convince you. So there's one example where we've really understood this in great detail, and that's what I'm going to spend a fair amount of this lecture series on. And this is not the case of AdS5 cross S5, but that's the low-dimensional cousin of this problem. And the low-dimensional cousin is that you look at AdS3 cross S3 cross T4. So you should think of this. So this is always 10-dimensional. So the 5 plus 5 is 10, 3 plus 3 plus 4 is 10. So this is another string theory. This is sort of the low-dimensional version of AdS5 cross S5. And in AdS5, the boundary is 4-dimensional, so the dual field theory should be 4-dimensional. For AdS3, the dual field theory should be 2-dimensional. So you expect the 2D CFT that is dual to it, and the 2D CFT that's dual to it is the symmetric orbifold of T4. And I'll explain to you at some stage later what exactly this theory is, but at this stage it's sufficient for you to know that it's an exactly solvable 2-dimensional conformal field theory that you have, again, under complete control. And the idea is that this is the analog of free superangles. So this theory I'm going to explain to you, and what we found, and that is what I'm going to try to explain to you, is a worldsheet description for this background, which is exactly dual to this theory. And because this is a regime where this theory is under control, and I'm going to write down for you a worldsheet theory that's under control, I can calculate everything I want on this side, I can calculate everything I want on this side, and then I can simply compare. And what I'm going to try to convince you of is that we've compared things and they match on the nose. So in particular, we can compute the complete spectrum here, then compare to the complete string spectrum here, and they match. And we can show that the correlation functions here reproduce the correlation functions here. So that goes a long way of really proving that these two descriptions are the same. And it's a very concrete description, and it involves things that maybe some of you are also familiar with. It involves affine Kac-Moody algebras and the like. It's representation theory. So that's what I'm going to spend a fair amount of my time on, trying to explain to you this correspondence in detail. Now, more recently, in fact, that's work that I've done together with Rajesh within the last year, is that we've learned that this description actually has a very natural generalization to the case of AdS5. So you can take this worldsheet theory, and there's a natural generalization to a worldsheet description for AdS5 cross S5 at the point where it is dual to free superangles. So what we've done is we've taken the lesson from AdS3, and there's a natural way of generalizing it to guess what the worldsheet theory is that it's dual to n equals to 4 superangles. And what we've managed to show is that it reproduces correctly the spectrum of free n equals to 4 superangles. Now this is at a much earlier stage of the development, and therefore I'm going to talk much less about it because there are many, many things we don't yet understand. So I mainly want to explain to you all the things we understand here, and then I want to indicate how this generalizes and open the ways of actually solving the problem I started out with. Yes?
Why does the worldsheet description depend on the target space? I thought it's kind of fixed for string theory.
No. I mean the worldsheet description, I mean, you should think of it basically, it's, I mean, ultimately there is one worldsheet description but that corresponds to all string theories, but when you change the background, you're going to modify the worldsheet description. So you should think of it, you have a CFT on the worldsheet, and you have exactly marginal operators, and as you exchange the worldsheet CFT, you change the background in which the string propagates. So depending on which background you look at, you're going to have a different worldsheet description. Ultimately, they should all be related to one another, but if you fix a specific background, you're going to fix a specific worldsheet theory. So there's a worldsheet theory for AdS3 cross S3 cross T4, there's a worldsheet theory for R to the 10, there's a worldsheet theory for, and so on. They are all ultimately connected in some complicated manner, but we are trying to identify the worldsheet theory that's exactly dual to a very specific dual CFT, so a very specific string background. And obviously it's unknown what the worldsheet theory is that's dual to 3 n equals to 4 super-mills, and what our work shows is that there is a natural guess for what this worldsheet theory should be, and I'll explain to you that there is some evidence that it seems to do the right thing. Okay, so this is by way of motivation, and now I want to start explaining to you. And so this theory I'm going to describe in two different ways. So I'll start with explaining to you AdS3 cross S3 cross T4. And the way I want to think of it is that this is take one. So this is like a movie, and we're going to have the take one of it, and then afterwards I'll give you take two. And then take 2 is the one that will naturally generalize to AdS5 cross S5, but take 1 is a little bit maybe more accessible for people. Okay, so what's the idea? Why is AdS3 simpler than AdS5? Now AdS3 is simpler because you see AdS3 is the space x1 squared plus x2 squared minus x0 squared minus x minus 1 squared is equal to, well, it doesn't matter. So I'll scale out I mean, I can, because it only depends on this ratio, I may fix this and then regard the string length as being variable. Doesn't really matter. I can also write r squared here. And what this can be identified with the group elements of the form x minus 1 plus x1, x0 minus x2, minus x0 minus x2, and x minus 1 minus x1 that have determinant equal to 1. So, so this hyperboloid can be identified with the group manifold of SL2R. So this is just real 2 by 2 matrices whose determinant is equal to 1. So therefore
minus 1 maybe in the top.
Well, that. Whether you put minus 1 or 1 is just whether you change the role of x0, x minus 1, x.
Yeah, but you also want determinant of g equal 1.
So maybe the way I've written it, then it should be minus 1, you're right. Yes, so this is just telling you that AdS3 is really the same as the group manifold of SL2R. And then S3 is the group manifold of SU2. So you can think of this as really being strings mapping into group manifolds. So that's the target space of this background. And therefore, if you know a little bit about conformity theory, there's a natural guess for what the worldsheet theory should be. It should be the Wessel-Minowitten model. So the Wessel-Minowitten model is basically, so the sigma model is conformal, and in order to make it conformal, you have to add the Wessel-Minow term. And the Wessel-Minowitten model is basically the conformal field theory with that target space. And the Wessel-Minowitten model that will describe strings on AdS3 cross S3 cross T4 will be based on the Lie algebra SL2R plus SU2 plus the Lie algebra of T4 is really 4 free bosons and 4 free fermions. So that'll be the Wessel-Minowitten model that you would think should describe this background geometry. Now, I've put these funny ones up here. So the ones up here are meant to indicate that these are n equals to 1 superconformal algebras. Or super affine algebras, I should say. So let me briefly remind you what these n equals to 1 algebras are. So what I mean by that is that this is, so you have generators which are j plus minus m and j3m. These are the generators of the SL2R Wessel-Minowit, of the affine Kac-Moody algebra associated to SL2R. So they'll satisfy the commutation relations j plus m, j minus n is equal to 2j3 m plus n plus k m delta m minus n, actually with a minus sign here, and then j3m, j plus minus n is plus minus j plus minus m plus n, and then the final one is j3m with j3n is minus k over 2 m times delta m minus n. So this is just the Kac-Moody and affine Kac-Moody algebra. So k is the central term, and I've chosen the convention that are natural for SL2R. So this algebra contains these generators, which are just the generators of SL2R with the Wessel-Minowit model. But then the fact that it has a 1 up here means that it has in addition fermionic generators that also transform in the adjoint representation. So you have, say, like fermionic generators psi plus minus r and psi 3r, and they will satisfy, they transform in the adjoint representation with respect to the SL2R, which is just meaning that j plus minus m psi 3r, say, is equal to minus plus psi plus minus m plus r. And so on. So they transform in the adjoint representation with respect to SL2R. So they sit in the adjoint. And then there are free fermions, so they just satisfy anti-commutation relations of the form that psi plus r, psi minus s is equal to k times delta r minus s, and so on. So you basically have a conventional SL2R affine Kac-Moody algebra, and then you have fermions sitting in the adjoint representation. They transform in the adjoint representation of the bosonic generators, and they're free fermions, so they just satisfy free fermionic anti-commutation relation. So that's what I mean by this, and similarly for SU2. So you have to look at the supersymmetric version of the affine Kac-Moody algebra. And then, as some of you may know, you can always decouple the fermions. So this SL2R algebra is really isomorphic to SL2R at level k plus 2 plus the three free fermions, which is to say that you can decouple the fermions from the bosons by defining these curly generators. So you define J plus M to be J plus M plus, and the correct formula is 2 over K sum over R, normal ordered product of psi 3 n minus R psi plus R, and so on. So you can subtract or add to the bosonic generator certain bilinears in the fermions, and then these bosonic generators, they satisfy an affine Kac-Moody algebra at a shifted level, and the level gets shifted up by plus 2, and then they commute with the fermions. Because I mean, basically what you're doing, out of the fermions you can build another copy of SL2R out of the bilinears, and then you are subtracting out the copy that corresponds from the bilinears in the fermions, and then that commutes with the fermions. So you get a decoupled system of bosonic generators and fermionic generators. So after the dust has settled, what this means is that this worldsheet theory is an SL2R affine Kac-Moody algebra at level k plus 2, and SU2 affine Kac-Moody algebra at level k minus 2, plus 6 free fermions, which I've decoupled, plus 4 free bosons and 4 free fermions. That's the worldsheet theory that you get after decoupling the fermionic degrees of freedom from the affine Kac-Moody algebra degrees of freedom. Is that clear?
You said that you shift by +2 and -2 in one case and the other.
That is correct. Yes, that has to do with the signature of the Cartan of the thinking metric. I mean, Cartan metric. So for SL2 you shift up by +2, and for SU2 you shift down by -2. Let's see whether that works. Now you can also work out the central charge, and when you work out the central charge, what you find that these two levels have to be the same. So this condition is equivalent to demanding that the total background has C equals to 15, which is the critical string condition for a superstring. So a priori you could have thought that the levels here could have been different. That would correspond to the fact that the size of the 3-sphere and the size of the AdS space is different. But the condition that this is a critical string theory, which means that the total central charge has to be equal to 15, ties these two radii together. And that's exactly what also happens for AdS5 cross S5. The radius of the 5-sphere and the radius of the AdS5 space have to be the same in order to preserve supersymmetry. And here you see the same thing. This is basically you should think of the level as basically being the radius of the space. The level going to infinity means the space gets very large. The level going to 0 means the space gets very small. So this is basically the size of the AdS space. That's the size of the 3-sphere. And they have to be the same in order for this to define a consistent string background. Again, I don't have time to explain why C equals to 15 is the correct condition, but believe me, that is the correct condition. So that is the consistent string background. Okay, so now...
Sorry, so you fix the size of you fix the size to be 1. So is this like inverse of string length?
Right, so I mean, this is the size in string length.
In string length.
That's what it means.
So the limit, you think limit where that's big?
No, so K is to be identified with R over Ls.
Okay.
So the supergravity regime would be K big. When you make K big, then this really becomes, as you know, then SU2 at level K for K goes to infinity really becomes, I mean, as Anton and others know very well, it becomes just the L2 space of functions on the group manifold. So the K goes to infinity limit is the sort of geometric limit, and K small is the limit where the size of the space gets very stringy, and we have to be in the regime where this is small. In fact, later on we are going to set K is equal to 1. That is the smallest possible. That's what lambda equals to 0 means. I mean, I said R should be of the same size as Ls, and that translates in this honest worldsheet description into the statement that a level is equal to 1. 1 is the smallest possible value, right? Because you know that this level has to be quantized, this has to be an integer for self-consistency, and then because of this condition, this is also quantized, because it has to be the same, and then the smallest value is K equals to 1. So K equals to 1 will be the magic value where things will start working.
I see. And the decoupling of the fermions happens for every K.
That
It's
happens for every
not
K.
only large K.
No, that is a totally quantum I mean, the reason is simply that, you see, when you have fermions transforming the adjoint representation, they make their own affine Kac-Moody algebra, right? Whenever you have fermions in the adjoint representation, you get a Kac-Moody algebra at the dual Coxeter number, at level of the dual Coxeter number. And basically what you're doing here is a coset construction. You're subtracting this SL2 from the other one, so that it commutes with the fermions, and that just shifts the level down by 2. So this is totally generic. This works for any K, also for K large, but in particular also for K small. And in fact, K equals to 1 is what we're going to aim for.
And what is C?
C is the central charge. Okay, so I haven't explained this, but this algebra also has a Virasoro algebra by the Shugawara construction, and C is the central charge of the total Virasoro algebra associated to all factors. So this gives you C equals to 6. So this gives you the C of this is equal to, well, if you work this out, because once you've decoupled it, this becomes 3k minus 2 over k plus 3 halves. That's the central charge of this guy. And the central charge of this guy is C is equal to 3k plus 2 over k plus 3 half. And this is C equals to 6. So if you add this and this and this together, you get 15, provided that the k's are the same. Because you see the relative terms cancel. This becomes a 3, this becomes a 3, 3 half, 6 gives you 15.
You have to subtract them. But what happened to the k? It's divided.
So, I mean, this is really k prime.
Okay.
And this would have been k prime. Then you ask for which value of k and k prime is the sum of 6 plus this equal to 15. And the answer is for k equals to k prime. And that means the size of the 3 sphere and the size of the AdS space are the same. Okay, so far I've just told you what the symmetry is, right? So this is basically telling you what's the symmetry of this worldsheet theory. But in order to describe the worldsheet theory, it's not enough just to say what's the symmetry. You have to say what's the spectrum. So what's the spectrum of this worldsheet theory? Now, for normal Westermino-Witten models, so people who are a little bit familiar with Westermino-Witten models, normally you say, okay, the spectrum of your theory, so the Hilbert space of my full conformal field theory, is the sum over all the highest rate representations, and I take the highest rate representation of the affine Kac-Moody algebra on the left, and I take the same representation on the right. That would be what people call the A-modular or diagonal modular invariant. That's sort of the simplest Westermino-Witten model. That's the Westermino-Witten model associated to the simply connected group. I mean, as Giovanni and Kuliain explained, the different modular invariants correspond to the different quotient groups of the group. So for SU2, that would be the correct Westermino-Witten model, and J would here run from 0 to k over 2. That's going to be the Westermino-Witten model description for SU2 for the bosonic pieces. And then the fermions just do their stuff. I mean, fermions only have one representation, right? There's just the Neveu-Schwarz vacuum and the Ramond vacuum, so you just tensor the bosonic degrees of freedom with what you get from the fermions. Now that's the true story for SU2. But for SL2, there is a subtlety. For SL2, that's not the correct answer. And the reason for this has to do with the fact that you see SL2 has a time-like direction, right? SL2, I mean, because of the hyperboloid, there is a time-like direction. So it should behave a little bit like string theory in flat space with a time-like direction. Now, if you know a little bit about string theory in flat space with a time-like direction, what you would know is that the L0 spectrum of the CFT is unbounded from below. It has to be unbounded from below, because otherwise you wouldn't get many string excitations. I mean, again, so you have to solve the Maxwell condition, L0 is equal to 1, say. But if the ground state has a bounded L0 spectrum, then you can't have many oscillators and still keep L0 equal to 1. So you get a real spectrum. L0 must be unbounded from below. It can't be bounded from below. Otherwise, you're not going to get the right degrees of freedom of string theory. So correspondingly, for SL2R, you can't just sum over the highest rate representations of SL2R. That wouldn't give you the right spectrum. And this is something which Maldaceno and Oguri understood at the turn of the century. At around 2000, 2001, they explained what's the correct Westermino-Witten model description for strings propagating on SL2R. And it is a little bit different from what happens for SU2, and that's worth explaining. So the correct answer is you have to sum over all the highest rate representations, but then you have a second sum over what is called spectral flow, and I'll explain to you what this is. And then you're going to get the spectrum will be of this form. So you don't just get the sum over the highest rate representations, but you also get the spectrally flowed images of the highest rate representations. And these will not be highest rate representations. So these are not highest rate representations. And I'll explain to you in a second why they are not. And that is important because this theory shouldn't have a bounded L0 spectrum. If it did, it can't possibly sustain the richness of the string excitations. Just like in flat space. In flat space, because of the Minkowski direction, I mean, you know, in flat space, the ground state is characterized by momentum, and its zero eigenvalue is p squared over 2, and that can be as negative as you want. It's unbounded in Minkowski space. And only from below. So likewise here, you can't just have highest rate representations. You have to have a representations that whose L0 eigenvalue is as negative as it goes. So you can have still many, many excitations to reach Maxwell condition L0 is equal to 1. That's a fact of life, and as I said, this was understood by Maldaceno and O'Gorman many years ago. So what is this funny set of representation you have to sum over? Well, this is easiest, the way to describe them is using this spectral flow idea. So what is spectral flow?
J is still half integer? Or?
Say again?
J is still half integer, or is it something else?
I'm being deliberately vague at this stage. I'll explain this in a second. But it should be run over all the right highest rate representations. Okay, so I can explain it right now. So what representations should you sum over? So if k is large, you know, you should reproduce the Denoise theorem. So therefore, the set of highest rate representations should be those that appear in the L2 of SL2R space. So for SL2R, the highest rate representations are the so-called discrete representations, which are the analog of what happens for SU2. So these are representations that are characterized by the property that they have a highest rate for the minus direction and then contain infinitely many states is J plus. So then the highest rate state is generated by all of these states. It's an infinite dimensional representation. And the Denoise theorem tells you that this J has to be bounded by a half less or equal than J less or equal than K minus 2, K minus 1. Plus 1 over 2. So these are the highest rate representations, but then in addition, you have the so-called continuous representations. And these representations are characterized by a spin, but they're by the states Jm, and J is of the form a half plus IS with S real, and M takes the values in Z plus alpha, where alpha is a number between 0 and 1. So this comes from the theta-Weil theorem based on the group SL2R. You can ask, if you look at all the square integral functions on SL2R, which matrix elements do you need? And what you need are the discrete representations and the continuous representations. So that's the set of highest rate representations you should be summing over. Because you see, in the limit k goes to infinity, that's basically going to give you back the Peter-Weil theorem. In the space k equal to infinity, as you'll see in a second, the spectral flow representations don't play a role. So that's the correct set of representations. Now, what is this spectral flow? Well, spectral flow is an automorphism of the SL2R affine Kac-Moody algebra. So sigma is an automorphism, and sigma acts in the following way. So sigma of W on J3n is equal to J3n plus k times W over 2 times delta n comma 0, and it acts on J plus minus n as J plus minus n minus plus W. So W is an integer, and it acts on the fermions in a similar manner. It acts on psi 3, it doesn't do anything on psi 3, and on psi plus minus, it shifts them up and down by W over 2. So what I'm claiming is that this is an automorphism. This is an automorphism of this algebra. And that's something you can simply check. So this is an algebra I've written down for you in detail. And what I claim is that this is an automorphism. So if I replace this if I replace any of these generators by this, the commutation relations get mapped into the commutation relations. So this is an automorphism of the algebra, and therefore if I have a representation, the automorphism induces a new representation. Now if the automorphism is inner, the new representation will be the same as the old representation, but if the automorphism outer, it will generically produce a new representation. So what do I mean exactly by producing a new representation from the automorphism? Well, it's the obvious construction. So what do I mean by sigma of W on Hj? So what I mean by that is that as a vector space, this is isomorphic to Hj, and I simply denote the elements by phi W, where phi runs over all the elements of Hj. So this is just the carbon copy of the original vector space, and then I define the representation, so JAN on the vector phi W is simply defined by applying the automorphism on JAN on phi. So I simply take the same vector space and I modify the action by applying the automorphism first. So that obviously gives me another representation, right? If you have a representation of an automorphism, then that produces for you a new representation. And for SL2R, so this is maybe familiar for people for SU2. For SU2, there is a similar construction, but for SU2, it maps a highest rate representation to a highest rate representation. It's not inner, it's outer, but it basically, so the analog for SU2, and this is something we are going to discuss in the exercise, Vit is going to discuss in the exercise session, so you can see this with your hands. For SU2, if you do the same thing, what you find is that this just exchanges the representation Hj with the representation Hk over 2 minus j. So it maps a highest rate representation to a highest rate representation, so it doesn't really do much. But for SL2R, it turns a highest rate representation into a representation that's not highest rate.
That's for a special W or what?
No, for all, essentially for all W's. I mean, so we are going to run W over the positive integers, but that doesn't really matter much.
SU2 case.
No, for SU2, I mean, this is for W equals to 1, and then for W equals to 2, it obviously doesn't do anything, right? But, I mean, you know this, right? This is the inner auto, I mean, this is the conjugate action with the loop that's closed in SU, that's closed in SO3, but not closed in SU2, right? So there's a loop. I mean, if you think of it in terms of the loop groups, you can ask maps from the circle into the group. And there's a map that doesn't quite close in SU2 because it ends on the central element. And so it's a loop that's closed in SO3, and therefore its adjoint action induces a map on the affine Kac-Moody algebra, and that's exactly what this sigma is for W equals to 1. And then for SU2, it basically just exchanges the Hj with the Hk over 2 minus j representation, and then if you do it twice, it doesn't do anything. But for SL2R, it produces new representations. In particular, it introduces representations that are not highest weight, which is important, because you see, we need an unbounded L0 spectrum. Otherwise, we have no chance of describing correct string theory on SL2R.
How is it I can't quite understood? Are you doing it also for continuous series or only for discrete series?
No, in fact, the continuous representations are the ones that are going to be the hero of this talk. Mm-hmm. Because as we'll find out, for k equals to 1, in fact, these are the only representations that exist. Mm-hmm. And in fact, they only exist for s equal to 0. But that I'll explain later, tomorrow, probably. Mm-hmm. So in principle, for generic k, you have both spectral flow, you have a generic k. I mean, all that I'm describing is at this stage for generic k. But for k equals to 1, what you will find is that these are the ones that really only survive. But spectral flow is the thing that really makes it interesting. And it's because it produces representations that are not highest weight, and that's where all the string spectrum will sit in.
Sorry, I'm still a bit confused, but continuous series is not highest weight to start with.
Ah,
right?
so when I say highest weight, I mean Virasoro highest weight. So what I mean by that is that the positive mode numbers kill it,
Okay.
but it's not highest weight in the affine sense. So what I'm saying is that after you apply spectral flow, they are not highest weight in the Virasoro sense.
Okay.
And the reason is that if you work this out, you see this induces an action on the Virasoro algebra, and the automorphism on the Virasoro algebra takes the form that this is equal to Ln minus W times J3n minus K over 4 times W times delta n comma 0. And you see, because these SL2R representations, they are unbounded in one direction, and as a consequence, this term makes sure that the L0 spectrum becomes unbounded. So because you see the SU2 representations, they are sort of finite in both directions. They are right. I mean, if you look at the highest weight space, there are a finite number of m's that contribute. For SL2R, the number of m's is either infinite or semi-infinite. And because you have in the Virasoro algebra, you get this term. If you work this out for L0, you see that you are basically going down infinitely, so the L0 spectrum is unbounded. So these are genuinely new representations that are not equivalent to the previous representations. And that's important, and that's a feature, that's not a bug. And it's a feature that replicates the fact that also in Minkowski space, the spectrum of the highest weight states is unbounded. The L0 spectrum, and you need this in order to get a good string spectrum. Okay, so I think my time is up. So what I want you to take away from this is that you can describe AdS3 cross S3 cross T4 in terms of the Wessel-Minowitsch model based on SL2R and SU2. For SL2R, you're going to have the new feature is that for SL2R you get this highest weight representations, but also non-highest weight representations. And the non-highest weight representations are most elegantly described by saying you get them from a conventional highest weight representation by applying an automorphism. That's just the trick of describing them. I could have also described them some other way, but this is the most convenient way of describing them explicitly. And what we'll do next time is we'll now study the string spectrum of this worldview theory. I mean, we ask what are the states that satisfy the Maschall condition and are killed by the positive mode. So this is the correct gauge condition in string theory. And then we enumerate the spectrum that this worldsheet theory has. And as I'll explain to you tomorrow, this reproduces exactly the spectrum of the symmetric orbifold of T4. You can calculate all the degrees of freedom that survive, and they match exactly one-to-one with all the states of your symmetric orbifold theory. So that shows you that the worldsheet theory really is exactly, at least as far as the spectrum is concerned, exactly equivalent to the symmetric orbifold theory. Okay, so I'll stop here.
Questions or comments? Of course, we can continue asking. Yeah.
Like like just because this is completely new stuff to me. So I would like to know whether there is some kind of like reading that, some kind of material that I could read before like tomorrow's lecture, so I can get a little bit on pace.
So which you mean you want to understand this Wessel-Minowitsch model background, or?
Yeah, or yeah, maybe like that.
Yeah, so no, I'm not sure. Witt is probably the best. I mean, you've been learning this stuff recently. So what did you find most useful?
So I think there is this paper of you with Latin and
Juan Yortaya. So there's a paper I wrote where we that's probably 2018, where we explained the SUSY description of this Wessel-Minowitsch model in some detail. So I mean, it's I've forgotten the archive number, but it's probably maybe 17. And it's actually 17. So it's probably October 17 or something. But there's only one paper I wrote with him. So
Okay.
yes.
You say that something will match very nicely, but isn't there some ambiguity in this step to say this is the worldsheet theory for this?
Absolutely, absolutely, completely.
Yeah.
And that's the reason, you see, I mean, I told you that Maldacena already described this in 2000. So you could ask, why didn't people do this before? And there's a whole story that goes before it that motivates us to look at the k=1 theory. And that has to do with the fact that a symmetric orbifold has this big W infinity symmetry. So the symmetric orbifold is much more symmetrical than you would think, and that tells you that you should correspond to a tensionless string theory. And therefore, that motivated us to look at the k=1 theory. Now, the k=1 theory is also a bit subtle. That's something I mean, Giovanni has probably spotted it. So he pointed out that for SU2, the level gets shifted down by 2, and for SL2, the level gets shifted up by 2. So if I start with k=1, I'm going to end up with SU2 at level -1. Now there I should be a little bit worried, because the SU2 level -1, I've left the unitary world, something bad has happened. So k=1 in this description is a little bit delicate. But I'll explain it anyway, because the gist of the argument you can see much more easily in this description. The honest description of the k=1 theory uses the hybrid formalism of Berkowitz, Waffer, and Witten, and then you have to do the Wessel-Witten model based on the Lie superalgebra PSU1,1/2. And that at level 1 is more honestly defined, and that is the theory that really exactly reproduces it. So there is some intuition of why that's the right theory. This is basically what I tried to sketch at the beginning. There are technical difficulties, which I'm sweeping under the carpet for the moment, and I'll address later on and explain to you how you do it more properly. But that was the block for many people. The other block was that everybody was focused on the discrete representations. I mean, the literature of SL2R with the Witten model, everybody, and absolutely everybody, only studied discrete representations. And nobody thought the continuous representations were worth looking at. And what happens for k=1 is that the continuous representations are the only ones that survive. So somehow people missed that part of the spectrum which becomes on the nose, that which reproduces the symmetric orbifold. But you'll see tomorrow why these representations, so this formula, together with this formula, the mesh shell condition basically spits out for you the spectrum of the symmetric orbifold in a very simple manner, and that's what I'm going to explain tomorrow.
Okay, I suggest to postpone possible further questions to the quarter break. Is it right? We now have a quarter break, and I think we need to descend to the ground floor again. And there, again, according to the rules, I think we're supposed to sit if you want to take off the masks. Well, okay, so thanks again.